Welcome to Hartman Math. This is lesson 10.8, graphs of polar equations. Typically, when we begin looking at a new equation and trying to graph it, we do a table of values. In our previous lesson, we looked and saw that in polar coordinates, we have r comma theta. Here are independent variables, going to be theta, so we're going to plug in theta. And based on our equation, we're going to find the r value that goes with that. And then we're going to plot those in a polar grid where we have concentric circles. R is 1, R is 2, R is 3, and we have our standard key angles. So we begin with 0. Cosine of 0 is 0 times 2 is 2, so r equals 2. And we would put that at an angle of 0, 2 away from the origin in the positive direction, r being positive 2. All right, cosine of pi over 6. So you're going to see kind of our key angles are going to go every pi over 6 is going to be our intervals here. So pi over 6, cosine of pi over 6 is the square root of 3 over 2 multiplied by 2 is the square root of 3. And that's about 1.7. So here's pi over 6, 1, 2, a little bit short of that, a little bit past halfway, right about here. It's going to be 1.7, so there's that point. Pi over 3, cosine of pi over 3 is a half, times 2 is 1, so here's our pi over 3, and we're going to go positive 1 in that direction, and we have a point. Pi over 2, cosine of pi over 2 is 0, times 2 is 0. So, since here's pi over 2, we are 0 away, anything where the r value is 0 is going to be at the origin. All right, 2 pi over 3, cosine of 2 pi over 3 is negative a half, times 2, negative 1. So 2 pi over 3 about here, and instead of going 1 that way, since it's r value of negative 1, we're going to go the other way. So this way, 1 unit. Cosine of 5 pi over 6 is the square root of 3 over 2, but negative multiplied by 2 is negative square root 3 over 2. So here is about 5 pi over 6. So not going that way, going the other way. This way, about 1.7 away from the origin. About pi, cosine of pi is negative 1 times 2 is negative 2. Here is pi. Negative 2 means don't go that way, go the opposite way, 2 units, and we're here. So we're right back kind of where we had our first one. In fact, if you go beyond that, you're going to see that we're kind of repeating ourselves. And we've got these points, and it turns out that it's a circle that fits those points right there, and that's the graph of our polar equation. So some of the special polar graphs that you're going to want to be able to recognize, identify, see some key characteristics of, we start with what I call limacons. I don't believe that I'm pronouncing that correctly. There's a French word there. So that is of the form, and it has different equations here, but a plus or minus, could be one or the other, b cosine theta, or r equals a plus or minus, b sine theta. A and B are distances. You have that. So that's how limacon is defined. And we have limacons with inner loops, so it looks like this. This is the cosine variety where we're symmetric about the x-axis in terms of our regular rectangular coordinates. So this is a cosine graph, and it's one in which the ratio of A to B is less than 1. So maybe it's 2 plus 3 cosine theta would be something like that. If it was 2 minus, it generally is flipped across that way. If it's sine, it's going to be going up the y-axis. That's limacon with an inner loop. A cardioid, so you can see a key point right there, Cardioid, so heart-shaped, cardioid is if A and B are equal. So maybe it's 4 plus 4 sine theta, although that would be turned. In this case, maybe it's 4 plus 4 cosine theta. If it's dimpled, a dimpled limacon, you can see here, it does not have that as a key point. So just kind of, it's very circular, but this side just pushed in a little bit. As if the ratio of A to B is between 1 and 2, so maybe it's 3 plus 2 cosine theta. That might be something there. And then our convex limacon, if the ratio is 2 or bigger, very similar in shape, but it just doesn't really have that pushed in part. Pretty just flat right there. So maybe that's like 5 plus 2 cosine theta, where the ratio is 5 to 2. Rose curves. Rose curves have the number of petals when n is odd. So maybe it's cosine 3 theta, n is 3, cosine 3 theta would have 3 petals. If it was cosine 5 theta, that would have 5 petals. However, when the n value is even, it doubles the number of petals. So right here, if n was 4, cosine 4 theta, then it's going to have 8 petals. If it was cosine 10 theta, it would have 20 petals. And the petals are equally spaced around the circle here. So this one, in terms of our angles, theta is 0, 2 pi over 3, 4 pi over 3. We're back to 6 pi over 3 being 2 pi, which is coterminal with 0 right there. And a value is the distance from the origin to the tip of the petal. And in this case, for n's, it does have to be greater than or equal to 2. Circles and lemniscates. We already saw kind of the circle. We saw the one that we did earlier, r equals 2 cosine theta, would look like this, where this distance is 2. That would be the diameter. And it is not centered here at the origin. Sine goes up the y-axis. Again, a value, if that's a 5, then it's from 0 to 5 right there. In terms of points, lemniscate looks like a figure 8. It's a little weird here, but sine is going to be symmetric about the line y equals x, this diagonal line. And it's of the form r squared equals a squared sine 2 theta. More popular is the cosine variety. The cosine variety is symmetric about the x-axis. R squared equals a squared cosine 2 theta, that being a lemniscate. So now that we have that information, let's see if we can kind of sketch some curves here. We see r equals a cosine n theta. We know this is a rose curve. The n value is even, so we double it to say that it's going to have 8 petals. Cosine is going to have one of its petals on the x-axis. It would be 3 away. So 1, 2, 3, the tip here. And then there's going to be 8 petals. That's one of them equally spaced. So that means every pi over 4, there's going to be the tip of a petal. So we kind of think of it in terms of, and they do not overlap. Overlap there, my bad. Rose curve. Example number 6, lemniscate. We see that r squared equals its cosine. So that's going to be symmetric about the x-axis. We recognize it as r squared, and it says cosine 2 theta. We definitely are interested in the A value, which is how far our tips the figure 8 away from the origin. And that's based on right here. R squared equals 4, so R is going to be 2, or A is going to be 2. So we're going to go 2 to the right, 2 to the left. Those would be kind of the tips there of our figure 8. And then from there, something like that for the lemniscate. So now we're going to kind of play around with polar graphs, polar equations. We're going to use a graphing calculator to do so, so grab yours. I'll grab mine in a moment. This is going to be, if you want to pause it here, we're going to do 2 different graphs on the same axis. And these are going to be our equations. So first we go to mode, and we're going to go here, make sure we're in radian mode, and we're going to change over to polar mode for our functions. We're then going to check our window. This gives us theta min, 0 is a good initial value there. Theta max would be 2 pi typically. We can actually extend theta min to negative 2 pi, theta max to other values if we need to. We shouldn't need to mess with the step. Our x min and max are going to be pretty standard, maybe just going with a scale of 2s on those. And then when we press y equals, those are going to be our values. Notice when we press y equals, it now says R1 equals, R2 equals. Typical polar equations, those are our values. Go ahead and hit graph. When you're ready, pause until you're ready. Here we go, graph. You appear, you're a beachgoer, to have a sand dollar. The next one we're going to look at, as we'll go ahead and now do an R1, so we can erase those. It's pretty complicated, so pause here, just kind of write this down, be ready to input it. Normally, if we're just going to write this, normally the sign to the 5th, kind of the theta would go here. But in terms of our calculator, probably best to write it like this. These are going to be your window settings that you want to use. Remember, just don't mess with the step there. We should be fine. Get this into the calculator. Hit graph. See what you got. What do you think we would call this polar graph? If you had guessed butterfly curve, that is exactly what we call this one. And if you're interested, here are a few other interesting polar graphs to explore on your graphing calculator. Pause it here if you want to write those down, work them through. That's going to be it for today. That's kind of the end of the Honors Pre-Calculus course. So probably won't see you next time. I'll see you around.